PhD from ETH Zurich, and he spent some time as a postdoc at Berkeley, spent some time at Oxford in England, and is now a faculty member at ETH Zurich in the statistics department.
Thank you. I want to talk a bit about the MinWise hashing scheme for regression and classification. I want to start with the 3 examples. Oh, yeah, I should say it's 24 over there. And I want to start with 3 examples that are interested in this whole area. Especially the first one, get explained, even though I can't report any extraordinary results on that yet. But it's an interesting project where you have a database of tens of thousands or 100,000 patients, and for each patient you know pretty good record of their medical history. So, for example, you know which symptoms they had in the past 10 years. Okay, is it better? So you know which symptoms they've had in the past, and you know, for example, which drugs they have taken in the past. And in total, the database contains about 15,000 symptoms coded for and 15,000 drugs. And so now when I mean sparse regression, I mean sparsity in the sense that, for example, each patient just has a few active entries in there, which is luckily the case. I mean, there's no patient in there who's had thousands of symptoms and has taken tens of thousands of drugs. It's only maybe 10 active entries. Or actually, I was surprised that most patients had hundreds of active entries. But still, it's far short of the total number of 30,000 you have in there. So when I talk about sparsity in this talk, it's really about sparsity of the data matrix X itself, not about a optimal regression vector. Kind of that doesn't necessarily have to be sparse here. And it raises kind of 2 questions, I think, in general. Kind of, is there a way to compactify, in a sense, the sparse data matrix X and get away with a regression problem or a classification problem on a much smaller dimension? And the second question I think it raises in general is, what do you do about interactions? Because, for example, for this data set, it has been used a lot for drug surveillance. So, for example, you want to know, well, maybe drug A is good to avoid a heart attack. Drug B is also good if you take it. But maybe patients who take drug A and B together, they really get a problem. And you wouldn't find out about this in a randomized controlled experiment. So a database like that is a great chance kind of to find out about it. The problem is only if you want to encode all possible interactions, for example, drug-drug interactions, drug-symptom interactions. In this case, kind of you would have to encode about 500 million of them. And for triplets, it's already 5 trillion, so you don't want to do that necessarily. And the question is there a way kind of to compactify kind of the matrix and get some kind of interaction modeling for sparse data matrices of this type? There are 2 more kind of where I'm going to show a few examples for a text regression or classification case, and it's kind of similar. So a document is encoded by words, and most documents just contain a small fraction of all words. So again, it's a sparse matrix. And a reputation scoring experiment, which I'm going to cover a bit later again. So for regression, the picture is a bit like that. You have a target response in Rn, and you want to model that as a linear model X times beta star. And the point is now that X is a sparse matrix, so the star entries really code for non-zero elements in here. And don't make an assumption that beta star is necessarily sparse. And then you've got some noise on top. And logistic regression would work in exactly kind of the same way. And the question is now kind of, is there a scheme to compactify it in the sense that you can write the sparse p-dimensional data matrix kind of as a dense matrix in just L dimensions now, where L is a lot smaller than P. And of course, you could use, for example, random projections or subsampling of some type. And we looked a bit into this MinWise hashing idea, which seems to be particularly interesting for sparse data matrices. And we wanted to understand a bit kind of why is it working. I mean, there are quite good empirical results on it. And we wanted to understand a bit kind of what it's doing. All right, so I should go back. MinWise hashing, kind of the idea is really very simple. So what you do is to get what you call a sketch maybe of the data is you permute your columns at random, say once, and then in the permuted order, you check from left to right, kind of where do I find the first non-zero entry, and then you note that number down, kind of which element kind of was the first non-zero one. And then you can repeat that for a new random permutation and do that L times. So the idea is that basically you aim for the Jacka index of two sets. So you can think about the sets Z1 to Zn is the Zi is the set of active entries for observation I. So it's the set of entries which are non-zero in the ith row of the data matrix X. And the interesting quantity is kind of the Jacka index, so it's the fraction between the size of the intersection between two sets Zi, Zj, over the size of the union. And the interesting thing, in a sense, is that if you take a random permutation of your data and you compute your MinWise hash, so you compute exactly kind of which entry is the first non-zero one in there, then the probability that you get a collision for two observations I and j is exactly equal to the Jacka index. And somehow you want to exploit that a bit kind of to say, well, say two rows which are really similar kind of, they will have a really high chance of getting exactly the same MinWise hash value in here. So here's an example. It's a smaller data matrix X. And I've written one permutation down on top, 3124. And now you check, for example, for the first observation, kind of you check, well, in that order, given by pi, where's the first non-zero entry? And for the first observation, you don't have to look far. It's already at the first point, so you write down a 1. For the second one, where pi is equal to 1, you have a 0 entry, so you have to go to the next entry, which is 2, and there you find an active entry, so you would write down 2, and so on and so on. And then you can do it for another permutation, which is now, say, 2413. So you do exactly the same thing again. For the first observation, you check in the first place, there's nothing there. Second place, there's nothing there. Third place, you find something, so you write down a 3 here, and so on. And for the next 3 observations, for example, the first entry is active, so you get a 1. And for the fourth entry, the first active entry is in place 2, so you write down a 2. And so you can do that as many times as you like, L times. And the idea would now be to use this dense data matrix M for regression in some way instead of your sparse data matrix X. So again, kind of you would imagine you can imagine the dimensionality of X maybe 1 million or tens of millions, and the dimensionality of M maybe just 1,000, something like that. The problem is only if you look at M, these are really factors, so there's no real meaning to it being 3 instead of, I mean, there's no natural ordering there. So the question is, what do you do about that? One strategy would be to say, well, for each column, I look at kind of what are the unique values I get, and then I code those as factors. And you can do that. The problem is only you don't know how many unique values you're going to get in a large database of, say, where you've got 1 million observations. So potentially, you could end up with a large number of columns, which would be unwieldy. And so the neat idea of B-bit MinWise hashing is to say, well, I take my data matrix M, And then I kind of randomly map all unique values into just 2 classes by just keeping the last bit of M. So, which would mean the 1 would map to 1, 2 maps to 0, 2 maps to 0 here, and the 3 maps again to 1. So for each column, essentially you divide into 2 blocks. And if you've got the same value, M, in here, they're going to end up in the same block. And if they have a different value, they might still end up kind of with the same value in here. Okay, and now you've got a binary data matrix M, and you can use that kind of to do regression. And it's not immediately obvious kind of why that should work, so we wanted to look a bit into that. And you can also extend this to b-bit, kind of where b is larger than 1, so you can keep more than the last bit. And actually, Ping Li, who has more or less invented that, he should be here, but I haven't seen him yet. So if you're here, can you raise your hand? But no, not. But I think he gives a talk tomorrow, so he can give you the. Sorry. Oh, have I done something wrong? No. Okay, and the complication is a bit kind of, if you want to study exactly this scheme, there are a lot of dependencies created kind of by the fact that the same M values always map kind of to the same last bit. And so what we said, well, we said kind of let's make that mapping into 2 groups kind of more explicit randomly. And what we call MRS map. And the advantages are kind of you don't have to decide really how many bits to keep. You can get a variable importance measure. And also you can deal with data matrices which are not binary but have continuous entries, which I think is helpful sometimes in practice. And it's less efficient to implement, so you pay a price for that. So, but it's not too bad. So the idea again, kind of, this is the workflow instance of b-bit MinWise hashing, and what we do is exactly the same. But now the mapping kind of from the unique values of M into the new data matrix S is explicitly random. So for each of these unique values, kind of you assign a random sign, either -1 or 1. And you're going to work with that. So for example, here in the first one, 2 maps to -1 is randomly chosen, and 1 maps to 1. In the third column, 1 maps to -1, and 2 and 3 map to 1. And then you keep essentially just the data matrix S, and you do linear regression or classification just using that data matrix in the end. And continuous variables can, in that scheme, easily be dealt with. So say you've got, instead of just binary entries, you've got a 4.2 entry there. Then you would just multiply that entry with the corresponding sign. So, oh, sorry, I left out a step, I think, here. The H matrix, I have to explain kind of that. Instead of M, which is the min of pi L, Zi, kind of, you can also keep the argmin. And it's a bit easier conceptually because the entries in H are really the actual variables, kind of, which were chosen as the, which had the first non-zero entry. So if you look here, for example, an H entry of 2 means that really the second variable came up first in the random permutation. And an H value of 3 and 3 means that this one was responsible kind of for the first non-zero entry in both of these random permutations. But it's exactly equivalent. It's just a maybe more convenient way to think about it. And so you can see, for example, here the third variable was chosen kind of for the 2 random permutations. So you can map this 4.2. You multiply it with the random sign chosen for the variable 3 in these 2 cases. And so you get your data matrix S, which is just the multiplication of a random sign times your actual data entry X, which now can be continuous. If this is too confusing, it doesn't matter. It's the binary case kind of contains all the important stuff, but I still thought it's important kind of that you can deal with continuous variables easily as well. And now you can do this, so you create your dense data matrix S, which, if X is binary, it's just contains -1s and 1s. And the question is then, well, can you find a regression vector B star in RL such that this is really close to the original problem if P is a lot larger than L? Okay, and if you can do that, then you're almost there, because then you just need to deal kind of with the estimation error on top, which is going to be small because L is really small. So this is kind of the crucial step. And if you think about it, you can ask yourself, well, say L is equal to 1, say I do it only once. Can I find a construction for the B star such that the expected value of the right-hand side is exactly equal to the left-hand side, so that I have an unbiased estimator, if you will, of X beta star? And there is a way kind of to do it. So I'm just going to deal with the binary case now, where X is binary. And so S, the matrix S, just contains your randomly chosen signs. And so in here, you've got your randomly chosen signs, where H1 is now the variable which was responsible for the first non-zero entry for the first observation, and so on. And B star kind of you can simply set to be Q times the sum of beta star K psi K. Now, it's important kind of you don't have to do that in practice, right? So, because you wouldn't know beta star, obviously. It's just a construction. And if you do that kind of and multiply it out, then you see, due to these random signs, in expectation, what you keep if you multiply psi h1 with psi k, in expectation, it's 0, of course, unless k is equal to h1. So you only keep this one term in there. And what you sum is the sum of k 1 to p, beta star k, the q still there, and then the probability that h1 is really equal to k. And now I've made this slightly simplifying assumption for the talk that, say you've got exactly q non-zero entries in each row, then the probability that a specific variable which is active is coming up as the first non-zero one is exactly 1 over q. So this q times probability h1 is equal to k actually is just 1. And it's only 1 if the corresponding entry in x is 1. And so you see that this term here is really equal to xik. And so it means what you get in expected value is just your x beta star. Okay, so it means if you just do it once, kind of your approximation is going to be unbiased. And so you just have to deal, in a sense, if you want to get an approximation bound, you just have to deal with the variance, which is induced kind of by the random permutations and random signs. And you can get a better bound if you weight things a bit, kind of. So you wouldn't want to put the full weight, for example, on a variable which comes up really late in the permutation, because the probability that that is going to be chosen as the min hash entry is really small. So you want to put most of the weight into the front, and actually you can choose the weights in an optimal way. And if you do that, then you see again the expected value is okay. And the bound you get for the approximation errors of the form 2k, then the L2 norm squared of beta star divided by L, where L is again the number of times kind of you do this whole operation. So the success is going to be tied to the L2 norm of beta star, which is, again, is a very similar result I mentioned that you would get for random projections, for example. Saying that if your signal is associated with a direction kind of which has a high variance, it's much easier to deal with that than if it's associated kind of with a low variance component. And so we wanted to look a bit at the statistical properties as well. For example, look at the mean squared error. And so you have to trade off a bit how large you choose L. So clearly, the larger you choose L, the smaller the approximation error is going to be, but the estimation error is going to go up, and you have to trade these two off in an optimal way. And if you do that, kind of you get a result that the mean squared error is going to go down at a slow rate of square root 2q over n, where q is again the number of non-zero entries you have in each row, times the L2 norm of B star. And here you've got an entry which is 1 if you pick L in an optimal way. And if you don't pick it in an optimal way, then you pay a price for that, because if you make it too low, the approximation error is going to go up. If you make it too large, the estimation error is going to go up. And I have to say that that is a result without any assumption on the underlying design X. And this is kind of also why you get a kind of a slow rate, which you would also get, for example, for the LSU type estimation if you don't make any assumption about X. And so in general, you would be consistent if P over n is going to 0, but you can be doing much better again if the signals associated come with a direction which has a high variance in X. Okay. For ridge regression, we get really similar results. The changes in the sense that for least squares estimation on S, kind of you have to be really careful how large you choose L. With ridge regression, kind of you can make L as large as you want, but then you have to be careful, obviously, about the tuning parameter. But if you do that right, the result is exactly the same. And logistic regression also comes out to be pretty much the same. So this is all assuming a linear model kind of for the underlying X. And what I mentioned in the beginning is a bit, can you do something about interactions? And clearly it's challenging. For example, if P is already 1 million, kind of, then to encode all interactions, kind of you would need an enormous data matrix X. So what we found surprising is really that MinWise hashing is dealing with some form of interaction fitting automatically. You don't have to do anything. You can do exactly the same procedure as before, and you can fit interactions with that. And I say it's doing it almost for free, because the price you pay is that you have to make your L larger, so you have to have a larger set of projections somehow. And the key thing is that obviously it's a nonlinear operation going on. So if you think about a single MinWise hash operation, what it might look like is that essentially you get almost like a random tree type operation, where in the first node you ask, is the variable which I picked first in the random permutation, is that non-zero? And if it's non-zero, then I would give as output the value of that random variable. If it is 0, I ask kind of the next variable in the randomly chosen permutation if it is 0. And I continue until I find kind of the first non-zero entry, and I return the value of that variable times the randomly chosen sign. So it's like a random tree. And this also makes it maybe intuitively clear why you can fit actually interactions, because in this case, for example, you can only get the value minus x2 if x2 is non-zero and the first variable is exactly equal to 0. So if you do that, you can write down an interaction model where you have your signal is essentially a linear term again. This is exactly the same as in the first part. And then you add interactions, which are now written down in this way. If you think about X as a binary matrix, then this model is encompassing actually all pairwise interactions kind of you can think of. And you get a matrix now theta star too. And if you define kind of a norm for this interaction model in this way, then the result you get is exactly the same if you replace the 2 norm of beta star with this L big theta star. So for example, if you have no interactions, then of course kind of you're exactly back to the old result. But the interesting thing is in the sense that suppose you have a sparse interaction model, so you just have a few non-zero elements in there, then this term is going to contribute a Q, and you get a Q here. And so if you look at how many projections kind of you have to make, so how large you have to choose L, then you have to choose L only as larger than Q squared rather than P squared. So which is obviously a big saving in the medical data example. Q's maybe 100 or 1,000 kind of, so you would have to do 1,000,000, which is a lot better than 10 to the power 12. Yeah, okay. This is just kind of then, I mean, the approximation error is here, and then if you deal kind of with the statistical part, again, obviously kind of you get exactly the same result as for the linear part, just that the 2 norm of beta star is again replaced by this L of theta star. So it's kind of surprising in a sense because you can fit interactions even though you just fit a linear model on S. I mean, well, in a sense it's not surprising, but when at the beginning we were surprised about it. And you don't have to create those interactions explicitly or code them up. It just happens more or less automatically. And the complexity saving factor is usually Q over P squared over the brute force approach, where brute force would mean kind of you have to code all interactions up, and you don't even have a budget for that, but then you have to compute your estimator kind of on this full interaction design as well. And as I said, kind of the price you have to pay is that you have to make a lot larger potentially than if you just fit a linear model in your axis. Variable importance is also something maybe of interest which hasn't been discussed a lot. So far it's mainly been about prediction, but sometimes it's still interesting. Kind of you want to know which variables were really important, or you go in and say, well, so what happens if I take this variable out? Kind of do my predictions change a lot or not? And in the general case, you can ask, for example, what happens if I set the kth variable equal to 0? How are my predictions going to change? And of course, if you have a linear model, then if you take the kth variable out, you just have your contribution from xk beta star k, where xk is your kth variable. And you can easily do this here. You just have to store 3 matrices instead of 1. So the S matrix is exactly the same as before, and now you have to construct the second one S tilde. And S tilde is constructed in a way such that in the MinWise hashing operation, you don't look for the first non-zero entry, but you look for the second non-zero entry, and you always write down the second non-zero entry. And you have to keep that matrix H as well in memory. And then you can say, well, f hat minus k is exactly like that. The reasoning being that you look essentially for operations kind of where the variable k came up as the first non-zero entry. And then you think, well, if it had been 0, actually, I would have picked the second non-zero entry. So if I multiply it in this way, I just replace for those times where the variable really came up as the first non-zero entry, I replace that effectively with a 0 entry and return the value I would have gotten if it had been 0. So it's a very easy way kind of to compute some kind of variable importance score if you want to, by not much more computational effort. And a really important point now, we have a lot of numerical results, but I don't want to bore you with that too much, just summarizing kind of the main points. One really important thing is in practice that you can aggregate that. So you can do that procedure once, and then you can do it again and again, and you can just average out over the results. And it helps a lot because the estimation error might stay the same, but your approximation error is going down because you average out kind of the randomness in the procedure, which is still there kind of if you just do it once and it's unnecessary kind of to have that still in there. Well, kind of trivial points, the predictive accuracy can decrease if you make L too large, obviously, because then you start to fit a lot of noise. And I would sum up the performance pretty much that in the absence of interactions, it's pretty similar to a rich regression on the full data set or a random projection type operation. And actually, I think there are reasons to suspect it might be very similar indeed from a theoretical point of view as well. The interesting thing is if you add in interactions, it starts to fit them automatically, and it's not as good then. I mean, if you have a really high signal-to-noise ratio, random forest is always gonna beat that, but it goes half of the way, say. But the advantage is, for example, if your signal-to-noise ratio is really weak, then random forest is gonna suffer a lot, and this is not gonna suffer as much. So it's like a compromise between a rich regression type estimation and a tree ensemble type operation. Okay, this is just an example for a data set kind of where you want to predict volatility based on text data. So it's text regression problem, and you've got about 4 million predictor variables, which are coding for words and bigrams. And you can check kind of how good is your forecast as a function of L, as a function of how many projections kind of you make. And here it's compared kind of with the zero added noise and then with added noise as well. And what you see here is the correlation between your forecast and the actual values as a function of L. So L is on that axis, and it's going up from 0 to 500. And red is kind of what we get kind of with this MinWise hashing scheme, and you see the correlation is increasing, then it's plateauing a bit. And blue is random projections, so it's working pretty much the same. It's a tiny bit worse here than random projections. And to test what would happen if the truth had been just a linear model, kind of we just took the same data matrix X and simulated an underlying linear model. And then you get a result which looks pretty much the same. So again, kind of the conclusion is, well, if it's a linear model, then actually it's doing very much the same as random projected. Now, if you include interactions, for example, in the original variables, then you do see that you can fit part of them. So the red one is now a lot better than the blue random projection point, as you would expect, because the latter obviously has no chance kind of fitting those interactions. The second and last example is also just a benchmark data set kind of where you want to detect malicious URLs based on some information, and the dimensionality here is you've got 3 million pieces of information. The sparsity is again that just a few thousand of them kind of might be active. N is 2 million, and now we wanted to compare it kind of not to random projections kind of, but to what happens if you use, for example, a rich estimator or a lasso estimator on the full data set. And we can only do that if we chop down the 2 million into smaller blocks, because otherwise kind of I can't do 2 million by 3 million on a laptop. And if we did that kind of for 10 days, then you see on the left is the performance of the MinWise hashing scheme. The dots correspond to these blocks, so which corresponds to days again, kind of where you want to make a forecast. And the performance is measured as a misclassification error as a function of L. So you see if L is above 1,000, it more or less converges. And this is compared to the lasso on the raw data, and you get pretty much kind of the same result. So the nice thing is now again kind of you projected down 3 million to just 1,000 dimensional space, and the result you get in terms of predictive accuracy is pretty much the same. In the middle is the result kind of if you aggregate the left results 20 times, so you do the procedure once and again and again and again and average the results. And the end result's going to be very much the same, but you need a much smaller value of L. And sometimes you can see kind of that actually you can get an overall better performance in this way. And compared to the rich data, to a rich regression on the original data, it is actually doing a lot better here. But on the whole, I would say if you could do a rich estimator and the model is approximately linear, you will get very similar results in the end, if L is large enough. Okay, so the conclusions are just that essentially, I think, well, it's an interesting scheme because you can fit a linear model if you want to in a fast way. If there are strong interactions, you're going to see them without having to do anything explicitly about them. It just happens more or less automatically. Thank you. Yeah, you mean in terms of, he's asking how it compares to a kernel approach, right? So you mean in terms of empirical performance or a theoretical? Empirically, I haven't tried, no. It would be interesting kind of to see. Well, you tell me, I mean, if anybody knows the answer, I'd be happy to hear it. Yeah.
I have a question. Early on in one of your rounds, you had some weights in the approximation error. So what are those weights? What do they mean and how do you use them?
This was just for the construction of the proof, kind of, so you don't need to know them in practice. This was just a way kind of to construct your hypothetical B star, but in practice you don't need to know them. It was just a way kind of to get a good bond.
Okay, so let's thank Nicolai again.